Hello, folks. Today we are going to start with a new venture on solid state devices. So, in this course, we will primarily deal with semiconductors and the physics behind the working of semiconductors. Now, this becomes a very foundational course for all those VLSA aspirants, and hence, mastering these concepts is very essential for them. Now, to begin with, let's start by revising some of the main ideas about atoms and molecules, which we have already learned in your high school. So we know that an atom has a positively charged center, which is called the nucleus, and you have electrons revolving around it, right? So yeah, so let me draw a very rough sketch, right? So these are my electrons. So we know that each electron out here is separated by a distance from the nucleus, right? And each electron is present in an orbit which is primarily called as a shell. Now, in physical terms, I can also say that this is like an energy level. Now, why is it an energy level? Because an electron which is located at a particular distance away from the nucleus has some sort of an energy associated with it, right? So the energy of this particular shell is, let's say, around here, but you know that this particular shell here is separated by a larger distance. So we have, let's say, the energy somewhere here. Fine. So this is my energy E1, and let's say this is my energy E2. Now, let's say that this particular orbit, which I am referring to, is the outermost orbit. Then we have a different name for that. What is it? You know, it's called the valence shell, and these electrons are called valence electrons, right? Now, you might have also learned this concept. What? If I supply some sort of an energy to these electrons, right? So, if I supply some sort of an energy to these electrons, then these electrons can excite to higher possible energy levels, right? Higher possible orbits. So, let's say that this is a possible orbit in which the electron can go, right? So let me draw that a little bit neatly. Yeah. Now the outermost but unoccupied here is called a conduction cell, a conduction shell, right? So as you can see, the valence shell is completely occupied while the conduction shell is empty. So this is in very simple terms about a valence and a conduction shell. So the points to note here is that valence shell is completely filled with electrons, while the conduction shell is completely free of electrons. Now, if I take some sort of a metal, let's say copper or silicon or rubber, whatever, right? So you know that these are available as solid blocks, right? You get iron bar, gold bar, for example. So you don't get individual atoms, right? You get atoms packed in a particular crystal lattice. Okay, this is called a lattice structure. Now, when atoms get arranged in a crystal lattice, now it will have a different behavior than what we see. Why? Because here you have only a single atom, right? But here you have multiple atoms and you have atom to atom interactions. So as a result, you cannot have individual energy levels for each of these shells. I would say, let's say that I have, this is one sort of an electron, I mean an atom. Let's say this is a different atom. kept closer, right? So the even energy level here for this atom is, let's say, here, but the even energy level for this atom is also the same, right? Because both are same atoms. Let's say this is a copper atom and this is also a copper atom. So both of these energy levels are exactly the same. But when these two atoms are kept close in a lattice, okay, then you can see that there is a variation in their energy, and this energy could vary slightly, especially when you have multiple atoms packed together. You will have a range of energies. What I mean to say here is that you won't get individual energy levels as you can see here. Fine. So when atoms are kept in a crystal lattice, what you see is not two lines like this, but instead of that, what you will see here will look something like this. Fine. Okay. So as you can see, yeah, I had drawn three levels, right? So let me draw one more. Let's say this is E3 and this is E2. Okay, so we can say that this is, in this case, the valence energy level, and this is my conduction energy level. Correct. So this level has a lot of electrons, right? The valence electrons, but this is empty. And I had already mentioned that this electron could excite. But if I look at the same scenario when atoms are kept in a lattice, it will look something like this. Okay. Uh, I should draw one more to make the idea clear. So let's say that this is my valence band. Now I call it as a band. Why? Because you have a range of energy. And this is called a conduction band. So as I have already mentioned, the valence band is completely filled with electrons and the conduction band is empty. And if I supply some energy, these electrons could excite to the conduction band. Right? Now, there are certain materials. Right? So these materials are called conductors. Now, if I look at conductors, what you will see here is that my, okay, what we'll see here is that if this is my conduction band, and let's say this is my valence band, this valence band and conduction band overlaps, right? So what I mean to say here is that in the case of conductors, this is my valence band and this is my conduction I mean this blue is my valence band, this orange is my conduction band, and these overlap at this particular region, right? So you know that this blue region, which is my valence band, is completely filled with electrons, right? Now, as a result of which, we can see that since my valence band and conduction band have an overlap, there are some electrons present in the conduction band even without I apply this particular energy, right? So, I can say that the conduction band in this case, which is that of conductors, is not free of electrons. There are some electrons from the valence band which share the conduction band. So these electrons does not require energy, right? So these electrons does not require energy to move into the conduction band, and hence they are called free electrons. Now why are they called free electrons? Because they are free to move around without application of any energy, right? Now, there are some materials which we call as semiconductors, about which we will learn throughout the course. Now, in the case of semiconductors, what happens is you have my conduction band somewhere here, and I have my valence band somewhere down here. But in this case, they have a small energy difference, and this energy is called the band gap. Okay, this energy level is means this energy difference is called my band gap. It's also called forbidden energy gap. Right. Now, if for example, if I take silicon, now this band gap is around 1.1 electron volt. Now we'll see what electron volt is. It's actually a unit of energy. So we'll learn about these in the coming videos. Now, similarly, we have conductors, semiconductors, and insulators. Now, insulators, yeah, the same story, but the difference is this band gap is very high. Okay, so it requires tremendous amount of energy. Okay, it requires tremendous amount of energy to excite an electron from the valence band to the conduction band. So it's kind of nearly impossible. I can't use the word impossible, but this gap is very high. Okay, you need to supply huge amount of energy. So we have seen how we can classify materials on based on the energy levels of their valence and conduction bands, uh, and that's the basic idea in the case of a semiconductor. Correct. So we will learn more about these in the upcoming videos.